Now we come down to compare those Null invariance measures. So which one is better? We know we probably can sense not all those Null invariant measures are created equal. So we want to see which one is better in all the cases. Let's examine the two variable contingency table on the transactions containing milk and coffee. Let's look at the case in this data set. So the first, you look at D1 and D2. D1 and D2, you probably can see the differences are only on the number of null transactions. But you also can see very likely milk and coffee should get together. They should be positive. In that sense, you can see all those 5 null invariant measures, they give equal value in the sense no matter how many transactions on the null part, okay, they do not change their value. And also they are very close to 1 in the sense these are possibly getting together. Then you look at D3. D3 means MC getting together is quite rare because they get alone actually is more frequent. In that sense, all their values are very close to 0. Then you look at D4. D4 says MC getting together or MC alone, they are all like 1,000, 1,000, and 1,000 cases. No matter how many null transactions, they actually got things right in the middle. This 0.5, 0.5, only Jacquard 0.33. Actually, this in Jacquard, this one means it's balanced. It's right in the middle. Then we look at trickier cases. It could be D5 and D6. D5, if you see this is 1,100 and 10,000 cases. So what you probably can see is from coffee point of view, like a coffee guy may say, oh, MC are likely getting together because they get along is 100 cases buying coffee, but not milk. 1,000 cases, they buying both coffee and milk. But from milk guy, they probably say, oh, they are very unlikely getting together because I got 10,000 cases buying milk, but not coffee, but only 1,000 cases buying milk and coffee. So in that case, you look at different measures. It's interesting. You see all confidence and Jacquard, they also say it's closer to 0. They are unlikely getting together. But max confidence says it's close to 1. They are very likely getting together. Then we look at Kruzinski said, I'm right in the middle because the tug of the war, each side is 10 to 1. Then cosine said, I'm a little prone to unlikely getting together. Now we change this one even more. This is 1,000 to 10 or 1,000 to 100,000. The coffee guy said they are very, very likely getting together. But milk guy said they are very unlikely getting together. Now in this case, you can see all confidence and Jacquard drop down to 0.01. And even cosine dropped down to 0.1. But the max confidence says, I'm very confident they are very close to 1 because they're very likely getting together. But Kruzinski said, I'm still in the neutral because this is 100 to 1. The other is 1 to 100. They have the equal ratio. So which one do you like? So probably we can see D4 to D6 are the real cases that differentiate the 5 null invariant measures. But we probably can see Kruzinski measure holds firm when in this very imbalanced cases, but the ratio is balanced on both sides, and it holds firm at 0.5. That looks interesting. But on the other hand, we also know those cases, some are very imbalanced. We may want to introduce another measure called imbalance ratio. The imbalance ratio is introduced in the sense the support of item set A and support of item set B, their differences play an important role in this imbalance ratio computation. Then you proceed for the same cases in the last 3, the Kruzinski measure holds firm at 0.5, but the imbalance ratio, okay, the D sub 4 cases is 0 because they are really balanced. And D sub 5 cases become 0.89. They are rather imbalanced. And D sub 6 cases, it is very imbalanced. So imbalance ratio really can show you, how balanced the two sides are. So we feel Kruzinski plus imbalance ratio, these two things getting together will present a clear picture for all the three data sets, D4 through D6. Because D4 is neutral and balanced, D5 is neutral but imbalanced, and D6 is neutral but very imbalanced. Okay. Finally, we are going to show you some real data sets, like a DBRB data sets. We want to look at co-author relationships. So let's look at this table. This table we got around the year 2007. We study the recent database conferences. We look at those authors. They publish papers and they co-author papers in database conferences. But you probably can see the interesting thing is, for example, you look at Hans-Peter Krieger and Martin Pfeiffer. Martin Pfeiffer got 18 papers, but all of them are with Hans-Peter Krieger. But Hans-Peter Krieger got 146 papers, 18 was with Martin Pfeiffer. Well, you can see in that cases, Kruzinski shows pretty strong value. That simply says these two authors are closely tied together in some way, but they are imbalanced as well. You can see that based on imbalance ratio, you can easily calculate their imbalance ratio is reasonably high. So in that case, you probably can easily judge Hans-Peter Krieger likely to be the advisor of Martin Pfeiffer. So using Kruzinski and imbalance ratio, we can easily find advisor-advisee relationships and close collaborators. In one research paper on finding advisor-advisees, we are really using those measures to find them with reasonably high accuracy. So finally, we will show you a bunch of papers. These are the papers quite representative on how to judge the correlation relationship, the different measures, including the interesting measure on the non-invariant ones, and the measure we discussed on the Kruzinski. Thank you.